It's January 1943, and the SS Schenectady, a brand new Liberty ship, is sitting peacefully in calm waters at the dock in Portland, Oregon. No storm, no torpedo, no enemy attack. And then, without warning, the entire ship breaks completely in half with a sound like a gunshot. The bow and stern separate, and the ship that was supposed to carry desperately needed supplies to the war effort is now two pieces of scrap metal. This wasn't a one-time failure. Liberty ships were cracking apart at an alarming rate, and the U.S. Navy had a terrifying problem. They were building these ships faster than they could figure out why they kept breaking. Until one welder proposed a solution so simple that engineers thought it was ridiculous. But it worked. Let me take you back to why this was happening. The United States needed cargo ships desperately. German U-boats were sinking Allied vessels faster than traditional shipyards could replace them. So the Maritime Commission came up with the Liberty ship design, a simple, standardized cargo vessel that could be mass-produced using prefabricated sections and welded together instead of riveted. This was revolutionary. Traditional ships took months to build. Liberty ships were being completed in weeks. The record was 4 days and 15 hours for the SS Robert E. Peary, but there was a problem nobody anticipated. Traditional riveted ships had thousands of individual rivets holding plates together. If a crack started, it would hit a rivet and stop. The rivet acted as a crack arrestor. But welded ships were different. The welds created continuous seams of metal. If a crack started in a weld, there was nothing to stop it. The crack could propagate across an entire section of the hull at incredible speed. The engineering term is brittle fracture, and it happens when steel loses its ductility in cold temperatures and under stress. The steel the Liberty ships were made from was fine in normal conditions. But in the North Atlantic in winter, with the hull under load from cargo and wave action, the steel became brittle. A small stress point, maybe a sharp corner in the design, maybe a flaw in a weld, would suddenly crack. And that crack would race through the hull like lightning. Image 2 prompt, close-up technical illustration of welded ship hull showing crack propagating through continuous weld seam, arrows indicating crack direction and speed, cross-section view showing brittle fracture. Cold steel, technical diagram aesthetic with dramatic lighting. By 1943, the situation was critical. At least 3 Liberty ships had broken completely in half. Dozens more had serious cracks. Ships were literally falling apart at sea and in harbors. The Navy convened emergency investigations. Metallurgists were brought in. Engineers examined every aspect of the design and construction. And they found multiple contributing factors. The steel chemistry wasn't ideal for cold weather, there were sharp corner designs that created stress concentration points, welding quality varied wildly between different shipyards, and welders were being rushed to meet production quotas. But here's the challenge: they couldn't stop building Liberty ships. The war depended on them. They couldn't redesign the entire class because hundreds were already built and hundreds more were under construction. They needed a solution that could be applied quickly to existing ships and incorporated into new construction without slowing down production. The engineers proposed various sophisticated solutions, different steel alloys, modified hull designs, improved welding procedures. All of these would help, but they would take time to implement. Then a welder came forward with what seemed like the simplest, almost stupid idea. He said, "What if we just drill a hole at the end of the crack?" The engineers looked at him like he was crazy. "You want to deliberately put a hole in the hull? That makes no sense." But the welder explained his reasoning. A crack propagates because of stress concentration at the sharp tip of the crack. That sharp point focuses all the stress into a tiny area. But if you drill a hole at the end of the crack, you eliminate the sharp point. You distribute the stress around a circular opening instead of concentrating it at a sharp crack tip. The crack stops because it has nowhere to go. The engineers were skeptical. But they were also desperate. They tried it on the SS Benjamin Huntington, which had developed serious cracks. They drilled holes at the ends of each crack. The cracks stopped growing. They monitored the ship carefully. The holes held. The ship made multiple voyages across the Atlantic without the cracks extending. It worked. This became known as a crack arrestor hole or a stop drill hole, and it was immediately incorporated into emergency repair procedures for damaged Liberty ships. But the genius went further. Engineers realized they could use the same principle proactively. They identified the high-stress points in the Liberty ship design, particularly around the corners of hatches and at the connections between deck houses and the hull, and they added what they called crack arrestor straps or doublers. These were reinforcing plates with rounded edges riveted or welded over the high-stress areas. The combination of the drilled holes and the crack arrestor plates transformed the Liberty ship program. Ships that would have been scrapped were returned to service. New construction incorporated the modifications from the start. The catastrophic failure rate dropped dramatically. But they didn't stop there. The Navy and Maritime Commission implemented a comprehensive program of improvements based on what they learned. They changed the steel specification to use a tougher grade of steel with better low-temperature properties. They modified the hull design to eliminate sharp corners wherever possible. Every corner was given a radius curve instead of a sharp angle because engineers now understood that sharp corners were stress concentrators. They improved welding training and quality control. They added more inspections during construction. Every Liberty ship was examined for potential crack initiation points, but the stop drill hole remained the emergency go-to solution throughout the war. Ships at sea that developed cracks could often make it to port if the crew could drill holes to arrest the crack propagation. Repair ships in forward areas carried drilling equipment specifically for this purpose. It became standard practice in the Navy, and the technique is still used in modern aircraft and ship repair today. Here's what makes this story remarkable from a survival perspective. The Liberty ship program built 2,710 ships during the war. These ships carried 75% of all cargo shipped overseas by the U.S. military. Without Liberty ships, the invasion of Europe might not have been possible. Without the crack arrestor solution, hundreds of those ships would have been lost not to enemy action but to structural failure. Thousands of merchant mariners survived voyages in ships that would have broken apart without that simple drilled hole stopping catastrophic cracks. The welder who proposed the solution understood something fundamental that the engineers had overlooked in their complex analyses. Sometimes the simplest solution is the right one. You don't always need exotic materials or elaborate redesigns. You need to understand the physics of the problem and apply the most direct fix. A crack needs a sharp tip to propagate. Remove the sharp tip, remove the crack propagation. The broader lesson here changed engineering practice permanently. The Liberty ship crisis led to the development of fracture mechanics as a formal engineering discipline. Engineers now routinely analyze designs for stress concentration points. Sharp corners are avoided in critical structures. Materials are tested for brittle fracture susceptibility. Aircraft, ships, bridges, pressure vessels, all are designed with crack propagation in mind because of what was learned from Liberty ships breaking in half, but it all came back to that welder's ridiculous trick. Drill a hole. Stop the crack. Save the ship. Save the cargo. Save the crew. Sometimes survival engineering isn't about sophisticated technology. It's about understanding the problem clearly and applying the simplest solution that works. The Liberty ships kept sailing, kept delivering supplies, kept supporting the war effort, because somebody thought to drill a hole. By the end of the war, the Liberty ship program had proven that mass production could work for complex structures if you learned from failures and implemented fixes quickly. The ships weren't perfect, but they were good enough, and they kept getting better. The combination of that welder's insight, the engineer's willingness to try a simple solution, and the rapid implementation across the entire fleet turned what could have been a catastrophic failure of the entire program into one of the great engineering success stories of World War II.